Okay. All right. So, hi everybody. Welcome to the special functions and number theory seminar. So, it's a great pleasure to introduce Surbhi Rai. She's a graduate student in IIT Delhi, working on a PhD, and her topic is expansion formulas for multiple basic hypergeometric series over root systems. On to you, Surbhi.
Thank you. Thank you for introduction. So hello, everyone. Welcome to today's talk. As we see, my topic for today is expansion formula for multiple hypergeometric series over root system. And this is a joint work with Gaurav Bhatnagar. This talk is basically part of a paper that has recently been accepted by the journal Advances in Applied Mathematics. I'll briefly introduce the results we have obtained, and I'll define and explain these terms in the coming slides. So Liu Ziguo is a Chinese mathematician who works in the area of Q series, hypergeometric series, number theory, particularly interested in the legacy of Ramanujan. In a series of work, Liu has derived various important transformation formulas and summation identities. So we have derived some multivariable transformation formulas over the root systems that extend Liu's transformation formulas for basic hypergeometric series. Further, we have generalized an expansion formula using the techniques of Xinrong, Ma, and Jin Wang. So throughout this, we have made use of AN and CN Bailey transform matrices and other summation and transformation theorems given by Gustafsson, Mel, Lilly, and others. So first we will look at the key formulas of Liu and their generalizations. For that, we need the notation of Q shifted factorial. For complex numbers A and Q, the infinite Q shifted factorial is defined as an infinite product of terms of the type 1 minus aq raised to j, where j runs over all the non-negative integers. Similarly, we define the finite q-shifted factorial, say a sub n, as a fraction of this form. Basically, a sub n for n a positive integer is a finite product of this form. When n is infinite, we require the absolute value of q to be strictly less than 1 for convergence of the infinite product. All right, and then when we have r variables, say to ar, then we would use this compact notation instead of writing it as a product of these factorials. Okay, moving to the main results of Liu. Here is one of the main expansion formulas. So let f be an analytic function near x0, then f can be expressed as shown here in this expansion formula. So this result clearly contains infinitely many Q identities, since we can select f in several ways. From this result itself, Liu has derived several other results by substituting special values for this function f. For instance, this particular one, he replaced f with the summation. Now here again, aj is a complex sequence, and we obtain this particular summation formula by simplifying the previous one. And as before, this result too contains many Q transformation formulas as special cases. We will look at a few of them soon. This is the third transformation formula. Here also we have a general complex sequence aj, and we see that this can be expressed as a double summation of this form in the right hand side. Let's look at the application of these three key results of Liu. So the first application would be this. As we saw earlier, how we could select different f to obtain different identities. Here is an expression obtained by substituting a particular value of f. So we put it in the first result to obtain this equation 1.4. Now, Liu has provided a completely new proof of the orthogonality relation of the Askey-Wilson polynomial using this particular equation 1.4. Moreover, Roseau's 6v5 summation formula can be recovered easily from it by replacing a few variables and simplifying this inner summation using one of the summation theorems. So we may regard the equation 1.4, that is this expression, as an extension of Roseau's 6v5 summation. Roseau's 6v5 summation is a non-terminating, very well-poised, balanced 6v5 series. Meanwhile, let's look at the definition for an RVS basic hypergeometric series. For R parameters in numerator and S parameter in denominator, such that the denominator is never zero, an RVS basic hypergeometric series is defined as an infinite summation of this form. So here 6v5 has 6 parameters of this form and 5 parameters here. And as we have seen in the theory of basic hypergeometric series, that Roseau's 6v5 summation has also proven to be quite useful. We can derive many important results using this. Okay, now looking at the application of the second result, here he replaced the complex sequence AK by few special terms, and further replacing and substituting certain variables, he obtained this summation formula. And using this summation formula, he obtained Hickey type series identities. These are just a few to list them. He obtained many Hickey type series identities. By definition, a Hickey type series is a series necessarily of this form, where the summation is over a subset of integer lattice z cross z. As we can see here, for instance, n is going from 0 to infinity, and the other variable j is going from minus n to n. And the summand is such that it contains a term -1 raised to some linear function of the summation indices. For instance, here it's n plus j, and q is raised to sum of a linear and quadratic function of summation indices, as we can see. So using the second result, Liu has derived multitude of Hickey type series identities. Now, in the third result, same as the last one, Liu substituted the sequence AK with a term to obtain this Q formula. He then put a few particular values to the variables to obtain this result. This proposition contains Watson's Q analog of Whipple's theorem as a special case. Thus, we may regard it an extension of Watson's Q analog of Whipple's theorem, which is given by this summation formula. So these results have apparently been shown to be useful in number theoretic contexts too. In particular, Chan and Liu, Wang and Key, and others have used them to provide Hickey type identities and identities for false theta and mock theta functions. All this work relies on 3 expansion formulas of Liu. Our work too is in the context of multiple basic hypergeometric series over root systems. This type of series has been developed systematically over the last many years. Previously, many of the central results of basic hypergeometric series have been extended. The goal of this paper is to lift Liu's expansion formula to multiple basic hypergeometric system over different root systems. And we observed that Liu proved his results based on a Q expansion formula, which he derived using Q derivative operator. However, the problem is that we don't yet have any technique to extend Q derivative operators to multivariable functions. Meanwhile, we observe that Wang and Ma used Q-Lagrange inversion, which, as Gesell and Stanton have pointed out, is equivalent to matrix inversion, and in this case, to the well-known Bailey transform. So Wang and Ma's approach can be extended to multiple basic hypergeometric series over root systems, since the Bailey transform has been extended to this context. So we look at the results of Wang and Ma, which happen to be a kind of generalization of the results of Liu, which we just saw. So this is the result one. In this particular result itself, we have an infinite summation in the left-hand side and a double summation in the right-hand side. So if we replace variables and set small b equals to 0, and and then we will obtain the very first result of Liu. Similarly, here in the second result, if we substitute a value of k, then we will obtain the other result of Liu. These results have been slightly rewritten for our convenience, and we see that these two are a generalization of the results of Liu. Okay. So now moving to our central idea of extending these results, we need a few basic background. So first is of matrix inversion. When we have a pair of infinite lower triangular matrices, say A and B, then they are called to be inverse matrices if they satisfy these properties, that A B I K summation, when I is running from K to N, is a delta function, delta NK, and similarly the other way around. So this is same as the usual matrix inversion, but just that it's we have n-dimensional matrices over here. Okay, so now let's say we have F and G, a pair of infinite inverse lower triangular matrices, such that the entries are given as this, given by this terms. The matrix inversion, this matrix inversion is equivalent to the Bailey matrix inversion. We derive this from the Bailey matrices by multiplying them with suitable diagonal matrices. Okay, then we consider the function fk of variable y and parameter a. The motivation for selecting this function is that when we replace y with q raised to m, it gives us the matrix entry of capital M F FMK. Okay, so our goal is to write an expression AY in this form. So we want to express AY as an infinite summation with this function Fk in terms of alpha k. So if we replace y with q raised to capital N, then as we saw before, the small function fkya reduces to the matrix entry fnka. Now, since F and G were inverse pair of matrices, by using matrix inversion, we can express alpha in terms of A. And so we obtain this, that alpha k now is a summation m going from 0 to k, gkma, aqm. Okay, so thing is that now by substituting this value of alpha k over here back to this expression, we can obtain an expression for a q raised to n, right? Now hope is that this, okay, now we want to express this ay in terms of ky and beta j. So hope is that this expression implies, by analytic continuation, an expression of the form we just saw earlier. So we have taken ay to be this form, and we obtain this from the last part. And so we had this from the last part. Now we substitute the value of a q raised to m using this new assumed ay in terms of beta g. So we have this summation over here. Now we can interchange the order of these two summation to obtain finally this expression a q raised to n is summation k equals to 0 to n fn k a, summation j equals to 0 to k beta j, summation m going from 0 to k minus j, and this. So one can take any function hjy as long as this expression is analytic in a disk around the horizon. So particularly the choice Wang and Ma made is that they took hjy to be small fjyb, which we just defined back, which was motivated from Bailey transform matrices. So using this choice, we find that this expression reduces to this finite summation. Here the matrices F and G are as we defined before. To get non-terminating results, we use analytic continuation if possible. That is, we replace q raised to n by y if it's possible, if the convergence conditions and things hold, and we obtain a non-terminating result. Okay, so simplifying this expression which we just obtained, we can obtain the results of Wang and Mark. So if we replace y by q raised to n, we will obtain the second result. And if we substitute a value for k of y, such that this inner summation can be summed using 3-2 sum, then we obtain the very first result of Wang and Ma. To summarize our central idea, we codify our approach in the form of this result. That is, if we have a pair of inverse matrices F and G, and then we select small fky, which is an analytic function in a disk around the horizon, which satisfies that f of k at q raised to n is related to the matrix entry f and k. We select ky, hjy, and beta j such that both sides of the following transformation formula are analytic in y in a disk, or y is equal to q raised to n for some non-negative integer and other terminating conditions, then this is the final expression we obtain. So the key idea in this paper is to use equivalent form of Bailey matrices. Equivalent form of Bailey matrices would give us different pairs of inverse matrices F and G to obtain this expression. Further, different choices of ky such that our inner sum can be summed using any of the existing summation formula, in particular, any of the existing 3-2 summation formula. Okay, so there are extensions of Bailey transform over the root systems AN and CN given by Mill and Lilly. We have non-terminating 6v5 summation due to Mill and Gustafsson, and more terminating 6v5 summations and several balanced 3v2 summations due to Mill and Bhattacharya. So using all of this, by substituting them in the obtained expression, we will give several multiple series generalizations which we have presented in this paper. So first of all, defining a multivariable hypergeometric series. It's a multiple series such that the summand Sk is a function of n-dimensional index k. And to be an n basic hypergeometric series, it needs to satisfy two conditions. First being that when we substitute n is equal to 1, it reduces to the basic hypergeometric series, the one variable hypergeometric series. And second is that it necessarily It contains the quotient of van der Waals determinants. That is a product of this form. X and X R x's are variables, Q is as before, and KR minus KS is also a variable. So in this section, we will look at the AN expansion and transformation formulas. So all of the results which follows, we will have this assumptions. For instance, a bold N of this form is an n-dimensional N, and we use this to show the component-wise addition. And similarly, and the parameters are chosen so that denominators are never zero. So this is the very first result which we obtain. This has been obtained using the Bailey pair of matrices, the AN Bailey pair of matrices. So as we can see over here in the left-hand side, we have an infinite summation. This is our van der Waals determinant term. This is beta j. Yeah, so here ky and beta j are general functions. We can replace them. And on the right-hand side, we have three summations. The first is an infinite summation. The second is dependent on the first, and in this way. And each of them have, like the first summation has again a van der Waals term. And here also we have a van der Waals term. And yeah, so here it's a infinite series expansion of in terms of the AN Bailey transform matrices. So we can, our next idea would be to replace ky in such a way that this particular summation can be summed using a 3-feet-2 sum. So let's look at the next result. Here we substituted ky with this term, which you can see here, the one before the summation. And this led to so using a 3-feet-2 summation given by Mill, we could sum the innermost sum, and we obtained this summation formula, Theorem 2. So, and one of the application of this is that a very well-poised 6v5 summation formula is contained in our last result. We have to replace beta j and a few variables to obtain the 6v5 summation formula. So if we look at the brief proof, we can we particularly used this AN balanced 3-feet-2 summation formula, which was given by Mill, to sum the innermost summation. Yeah. So similarly, we have given the different choice of ky. For instance, here it's a product r equals to 1 to n axr aqxr nr aaxr 1b bqxr nr. We obtain a similar but different result. This time it's a finite sum on both the left-hand side and the right-hand side. This is a dominating series of this type. So, and we used a different 3-feet-2 summation to obtain this result. Here again, if we replace beta j by suitable values and substitute them over here and replace a few variables, we will obtain another 6v5 summation formula. Okay, so that was about the AN expansion and transformation formula. In the next section, which is CN and DN expansion and transformation formula, we give some variation of the previous formula. Now the series involved contain terms that are a mix of terms which are usually associated with AN, CN, and DN. So here, Okay, so to obtain this, the proof is on similar lines with the proofs for the theorem 1, which was based on AN. And so here we used a pair of inverse matrices F and G, which are an alternative expression for CN Bailey transform matrices. And yeah, so we can look over here that how this sum has both terms from AN and CN. The left-hand side is an AN kind of summation because it just contains a quotient of van der Waals determinant, while on the right-hand side, the very first summation contains this product included with this one product R equals to 1 to n, and this makes it a CN type summation. Again, here the term is AN type. So it's a mix of these things. So we obtained this. Similarly, we obtained theorem 5 by substituting a value for ky here in the last result. We obtained this. We used a summation theorem, a DN352 summation theorem to sum the innermost sum, and we substituted this particular product for k of y to obtain this result. So we have two more theorems. One is an expansion formula where the left-hand side is an AN series and the right-hand side has a mix of CN and DN type factors. The second expansion theorem of this section transforms a CN type series into a series which mixes elements of an AN series with DN series. So the last theorem contains a CN non-terminating 6v5 summation due to Gustafsson. So we can replace beta j accordingly and substitute a particular value for few variables to obtain the 6v5 summation. And yeah, similarly, we can transform CN type series into a series which mixes them further. Okay. Next, we look at an AN extension of the third result of Liu. This computation is a mild variation of the previous proofs. So here we have obtained a terminating series. In certain situations, we can replace q raised to nr, which is here, by yr to obtain a non-terminating result. So this is one of the version of extensions of third result of Liu. So here it's a finite summation in the left-hand side and a finite summation in the right-hand side. And yeah, so if we put for n equals to 1, small n equals to 1, this would give us exactly the third result of Liu. So in this paper, we have seen several multiple series extensions of the general results of Wang and Ma, which in turn extend Liu's useful expansion formulas. As we saw, the approach which we used to formulate our central idea, it brought Liu's expansion formulas within the methodology of Bailey transform matrices. We listed 3 extensions of the second result of Wang and Ma and 4 of the first result of Wang and Ma. Our extensions contain several of 6v5 summation theorems over root systems. There are additional summation theorems given by Mill, which hint towards additional results of this nature. In addition, there are many possible applications and useful spatial cases in Liu's papers that can be extended to multiple series, and we're right now working on them. Yeah, so
Thank you. It was very fast. Any questions or comments?
Hi, Surbhi. Just wanted to say it was a nice talk.
thank you, sir.
So any comments or questions?
Okay, hi. I have a small question.
Yeah. Yes, sir.
Hi, Surbhi. It was a nice talk. So
Thank you,
I
sir.
wanted to ask, you have mentioned a lot of root systems. I mean, you were talking about root systems, but you mentioned about AN from my, or did I miss something in your talk that you were talking about other root systems also?
Yeah, we are talking about AN, CN, and DN.
Okay. So what was this CN and DN thing? If you could just quickly summarize.
Yeah, so CN, as I'll show you in one result. So basically, we are determining them with presence of terms of special forms. Like AN had a quotient of van der Waals determinant. CN is such that it contains. I'll just, yeah. So here, as we see in the right-hand side summation, the very first sum itself, it has a product 1 minus q qr minus ks xr 1 xs, and similarly the second term, and this product r equals to 1 to n 1 minus a xr square q 2 kr upon this. So this whole together makes it a CN root system.
I see. Okay.
So, can I add to that? Surbhi?
Yeah. Yes, sir.
So, Krishnan, there is a formal, if you look at the roots, just the EI minus, so formal exponentials of the root. So, just EI minus EJ or ER minus ES, then ER plus ES, and then 2ER. There is some formal relationship. So, early results in this area, they all seem to be motivated by saying that if there is something for this group, then there is something for that group, and so on. And later on, we sort of, like Surbhi has sort of mixed the two or three, so it's not clear that they are really have
Coming from one group or something.
Yeah, but still there is a useful classification to remember, to understand that, okay, if you've done for AN, then there should be something for CN. Is there something for DN? Is there something for G2, and so on? So and also ultimately they got some Jacobi triple product extensions by McDonald was what connected this AN business. So Milne proved, given proof of McDonald's Jacobi triple product identity using a binomial theorem for AN. So then, so earlier he used to call it over UN plus one unitary group. Then he started calling it over root system. So I mean, but so it seems to be there's this formal connection, but it's not 100% clear what the theoretical reason.
Like in this case, you may not have necessarily looked at if there is any connection with the group.
Yeah, you don't know, but some symmetry exists, and there are some. Some of the symmetries seem to be similar. I mean, of these terms, the symmetry seems to be called a symplectic symmetry by physicists.
Okay, nice. Thanks. Okay, that answers.
Yeah.
You mean McDonald's work in Inversion, that important paper?
72 paper, yeah.
Right.
The famous paper where D.N. Verma wrote a review, that paper.
Right. Also, it contains proof of his generalized Jacobi triple product identity just using binomial theorem.
No, using Milne used his AN extension of binomial theorem to give. So Jacobi triple product can be proved using a terminating form of this thing, right? Q binomial theorem. You know that, right? I mean, you go from minus n to n and then take the limits and so on.
Yes.
So similar calculation Milne did with his binomial theorem and got the AN McDonald identity. I think that is where the connection happened. So this was some paper in I don't know 1985 or something. Yeah. So I mean, That was the starting point when the people started calling them A and B and C N. And so also I think Surbhi didn't mention that Michael Schlosser had some has some 6v5s which are not captured yet
Yeah.
in these. So all these results can be motivated if you specialize this betas to be delta function, you get a 65 result. So the results are basically okay. If there is a 65, then there must be a result of this kind. That was a motivating factor of listing all these guys. So in particular, if Gustafson had if there was a non-terminating 65, then that should show up. If there's a terminating 65, that should show up, and so on. So that's why there's so many results. And I think there's some still pending, right? Which she plans to include in her thesis.
Yeah.
Okay. Any other questions or comments? All right, then let's thank the speaker and